Now, why am I talking about this? Well, again, remember, mathematics is first and foremost going to have a language that it's expressed in, and that language will be a formal grammar. But then also, there's something to observe. So here's a theorem. And this is why I've been saying decision problems and languages interchangeably. So a language L is specified by a formal grammar, specifiable by a formal grammar. What do you think I'm going to write next? Well, I mess up my M's. If and only if it is, say it with me, computably enumerable. We're all shocked. Why are we not shocked? Well, what are we doing here? In both cases, when we specify a decision problem via a Turing machine, we are specifying an infinite set via a finite string that I can interpret a specific way to generate a set. That's exactly the same thing that I'm doing here with languages and formal grammars. A formal grammar is a finitely definable thing that I can use to list out elements of a language. And remember, you might be a little confused by the enumerable part here. Oops. The enumerable part here. Like, why isn't it just computable? Why is it computably enumerable? Because remember I mentioned before that in some sense the class RE, the set of all computably enumerable languages, has a more natural association with Turing machines than the computable ones. The computable languages have a very special class of Turing machines. You can't say every Turing machine gives you a computable problem, but you can say that every Turing machine gives you a computably enumerable problem. And I can say the exact same thing about formal grammars, but that's more obvious. Every formal grammar gives me a language. That's the whole point. But I could say the same thing about Turing machines. Every Turing machine gives me a language too, or at least something that I can interpret as a language. And so, if Turing machines truly are like everything that I can do on paper, then this should not be a surprise. The fact that this is true. Why is it that every language that's specifiable by a form of grammar is computably enumerable? Well, look at all this. I just did it on paper. I did it with a pen and paper. And so by the Church-Turing thesis, it's computably enumerable. That's it. That's all you have to say. I'll type it out. There's a little bit of extra things to say. What I should technically say out loud is that I should enumerate over all the symbols in the alphabet. I should enumerate over all the rules, and then I can specify an algorithm by which I can kind of do derivations one at a time and kind of go through a comprehensive listing out of every derivation. But I can do each possible, but each single derivation is a computable thing to do, and therefore I have a computably generated list of all of the languages, and therefore the language itself is computably enumerable. So that's what you would say by the Church-Turing thesis. Let me type that out. So, given a pencil and paper, I can list out the derivations of all words in a language given by a formal grammar, one at a time. Therefore, by the Church-Turing thesis, any language given by a formal grammar is computably enumerable. That's the one direction of the proof. That's the A implies B part. If and only if specifies A implies B and also B implies A. Now this is a little more complicated. A bit more involved. I don't want to say complicated, a bit more involved. I mean, they're both kind of involved if you want to do an actual proof without the Church-Turing thesis, but we're not squares. We're not going to do that. So this direction is a bit more involved. But it's really not saying as much in terms of its depth. All it's really saying is, what does it mean to have this direction? What I'm trying to show here is that if it's computably enumerable, then it can be specified by a formal grammar. And so there is a kind of tricky, elegant process of like taking a formal grammar and like making a Turing machine out of it that gives you derivations and stuff, and it's kind of fun. But really all we're saying with doing that is that this definition of formal grammar um, is where I can stop the conversation about formal grammars. This is the top of the Chomsky hierarchy. It is, I don't need to specify anything else. So really, all it really says to show that if it's computably enumerable that it has a formal grammar, then what that really means is that I defined formal grammar in a powerful enough way that it gave me the most powerful possible grammar that I could define, i.e. the definition is correct. So it's not really a deep statement. It really just means I defined grammar well. So let me say it like this. This is saying that this direction says that specifying languages by formal grammars is just as powerful as specifying them by Turing machines. So what this really, I'm not going to prove this direction. So what this direction says, implies, is that my definition of a formal grammar is comprehensive enough to give, the biggest possible class of languages specifiable by finite grammars by some kind of set of rules, some kind of rule system, right? All this is really saying is that, this is the best possible rule system for defining languages because Turing machines are the be-all end-all of pencil and paper processes, of which formal grammars are just one particular kind. And so what we're saying here is that you can kind of almost think about the formal grammar definition as a model of computation, and as a model of computation, it is Turing complete. So yeah, I mean, that's why I can think about, that's why sometimes I say languages and sometimes I say decision problems, because they're kind of the same thing. Any infinite set, any infinite set of strings I can think of as a language or a decision problem. And so this is our first of several observations that are going to be of this type. And when I say of this type, what I'm really saying is confirmations of a claim that I made in the last video, or the video before that, which is that what kinds of infinite sets are specifiable by finite means? The computably enumerable ones. In other words, to say finitely describable is to say computably enumerable. And that's kind of the main point I want to make. Let me wrap up the video with that. So, moral of the story. Finitely describable means computably enumerable. We're going to see more examples of that. But if I can describe an infinite set finitely, then that set has to be computably enumerable. That's the moral of the story. Not even just a fact. It's just like, if I want to talk about finitely describable things, then I'm really talking about computable enumerable things. That's the moral of the story.